Welcome back to Applied Mathematics. In this video, I want to talk about planar systems. Let me get my head out of the way, and let's see if we can get enough vocabulary to understand what I'm talking about with that title. A system of equations is a collection of several equations, each using the same variables. A solution to the system is a collection of values for the variables in the system which satisfy every equation. So you want the same variables, plug in the value of x, the value of y, the value of z, and so on into every equation in the system, and all of the equations work out to be true. As a general rule, there should be the same number of equations as variables to expect a unique solution. That's not a guarantee. If you go further in the study of mathematics, the branch of mathematics called linear algebra studies this question fairly extensively. How do you know that a particular system is going to have a unique solution? Well, it's necessary that you have the same number of equations as you have variables. If you have too many equations, then you end up with what we call an over-constrained system where there is no solution. If you don't have enough equations, you will end up with what we call an under-constrained system which has infinitely many solutions. So there is a sweet spot. If the system is poorly set up, it's possible to have an over-constrained or an under-constrained system that still does have the same number of equations as variables, but it's a lot harder. You can usually stumble upon a system that has a unique solution just by following that one basic rule. All right. So, one last definition, and we are at our title. A planar system is a system in two variables. A planar system, usually we're going to use x and y, and when we have an equation in x and y, we can graph the equation on the coordinate plane. That's why we call it a planar system. Planar systems are nice because the graph can be the end-all be-all of solving the system. So for example, let's consider the system 2x minus 5y equals 1 and 4x minus 3y equals 9. If we graph these two equations, say using computer software like Desmos, we can see that the equations both give us lines. For the sake of simplicity, in this lesson, I'm going to stick with linear equations, although we can use nonlinear equations as well. And the interesting thing that I want you to notice here is that these two lines intersect at one point. And that's exactly what we're looking for. The graph of an equation is the collection of every ordered pair that is a solution to the equation. So every single point on the blue line is a solution to the equation 2x minus 5y equals 1. Every single point on the orange line is a solution to the equation 4x minus 3y equals 9. The place where those two lines intersect each other is the place that is a solution to both of the equations at the same time, which is exactly what it means to be a solution to the system. And when you graph a system of equations in Desmos, it notices those points and it makes them clickable. You click on the point and it gives you the coordinates for that point. The solution to this system of equations is the point 3, 1. And we're not surprised that there is a unique solution, because this is a system of equations in two variables, and it is a system that contains two equations. Two unknowns, two equations, one solution. All right. Well, that seems easy. Computers are able to solve systems of equations in two variables for us without much thought or effort. When it comes to higher order systems, well, computers are still able to solve them for us, but that's where things get tricky. And for relatively small systems, it's honestly faster, if you know what you're doing, to solve the system by hand than to go to a computer. So we are going to learn how to work through solving this system of equations by hand. We're going to extend that onto relatively small systems, and just know that when you're dealing with a system in two variables, it's very easy to get computer software to graph the system and give you the solution that way. When you're dealing with exceptionally large systems, I've done some work in my research that has led me to working with systems of 50 equations in 50 variables. And that's just a normal thing. And at that point, it is well worth the time to write a computer program to solve the system for me. But when I'm dealing with three variables, 4 variables, things like that, I tend to want to do it by hand. First of all, because I'm a glutton for punishment and I think that that is fun. But honestly, having become comfortable with it at a time when computers really couldn't do it anyway, or computers that could do it were well outside of my price point as a middle school, high school, college student, it's faster for me to be able to do it that way. If you're not convinced by that argument, the other argument that I have for you is that somebody has to know how to program the computer to write this code in the first place, and so we have to keep teaching it so that the skill isn't forgotten. All right, but let's look at this system. I'm going to use the process known as elimination. The method of elimination is almost always the best approach when you have your equations given in standard form, like these ones are. And the way the method of elimination is going to work is we're going to look at the coefficients, and we're going to look for the least common multiple between one of the sets of coefficients. In order to keep track of what we're doing, I'm going to go ahead and name these equations. I'll call them A and B. And what I notice is if I multiply equation A by 2, then the coefficient on x is going to be 4. And I could leave equation B alone, but I like doing something to everything. It makes me happy. So I'm going to multiply B by -1. When I do that, I will have 4x minus 10y equals 2. Just multiplying left and right side of that first equation by 2. And then multiply left and right side of the second equation by -1. I get -4x plus 3y equals -9. Now here's the step that everyone looks at and panics about. I'm going to add these equations together. The addition rule of equations says that if you have an equation that is true, you can add the same thing to both sides of the equation. No problem. We've used that to solve equations many times up to this point in your mathematics career. But if you have a second equation, let's say that C is equal to D, then by substitution, it's just as true to say that A plus C is equal to B plus D. That's what we're doing here. Our A is 4x minus 10y. Our B is 2. Our C is negative 4x plus 3y, and our D is negative 9. And we can add A plus C, we can add B plus D. 4x minus 4x is 0x, which is just 0. Immediately, the x variable is eliminated. That's why this process got the name it got. Then I have minus 10y plus 3y. All told, that's minus 7y. On the right-hand side, I have 2 minus 9, which is negative 7. Divide both sides of the equation by negative 7, and I get that y is equal to 1. If the system was a little bit more complicated, I might give this a name, but I'm just about done, so I'm just going to run with it from here. I now have my y coordinate. I still need my x coordinate. To get there, I need to go back to one of my original equations. I'm going to choose the second equation, 4x minus 3y equals 9. I'll remind myself that this is equation B, and I chose that one because it's the one that's still entirely on the screen and I remember what it is. I'm then going to plug in my value of y, and solve for x. Doing so gives me that x is equal to 3. My solution is a point on the coordinate plane, so I should present it as an ordered pair, x comma y, 3 comma 1, which is, I remind you, exactly what Desmos told us the solution was going to be. So we just took a lot of time to get to exactly what the computer told us without having to think at all. Again, I know sometimes that feels a little bit strange as something you might want to consider, but I think that the benefits are there. There are times when this is incredibly useful, and something that literally occurred to me while I was doing that example that I didn't mention earlier. There are going to be times, if you continue in the study of mathematics, where you're going to want to do this same process, but instead of having numbers, you're going to have literal equations with more variables and more parameters everywhere, where there's not anything you can put into the computer in order to solve it. All right. But let's look at another example. Three x minus 5y equals 2. Y equals 3/5 x plus 4. I wanted to go through this example because it's a great example of a problem where instead of using elimination, I would use a different method called the substitution method. I want to use the substitution method here because one of the equations is already solved for y. That means I can take that value of y and just plug it into the other equation. So I have 3x minus 5, and instead of y, I'll write down the value of y, 3/5 x plus 4. distribute, simplify, and in this case we get a very strange result. I get that negative 20 is equal to 2, which I hope you will agree is false. This has nothing to do with the fact that we used the substitution method, and everything to do with the particular equations that we were looking at here to start. If I go to Desmos and I try to graph this system, you will see that what we have is two parallel lines. Two parallel lines are lines that never intersect each other. And if they never intersect each other, there can't be a solution to the system. So there is something very interesting that can happen. And I feel like I'm trying to invent reasonings at this point, but this is another reason that it's worth understanding how this process works by hand. Because if you're using something like Desmos and you're trying to graph your solution, how do you check whether the equations are actually parallel to each other or just very close to parallel to each other? And if you zoom out far enough, you will find an intersection point somewhere along the line, right? If the solution was at the point where x equals 75,000, well, the graph is going to look like it's parallel this far out, and you have to zoom out quite a bit to see anything that resembles intersection at all. So it's a thing that can happen, it's a thing that will happen. Understanding it and being able to take it into account is something interesting that we have to think about. All right, so we have the substitution method, we have the elimination method, we have cases where there are solutions, we have cases where there are not solutions. Jason paddled his canoe 24 miles upstream in 4.0 hours. It took him 3.0 hours to paddle back. Assuming Jason kept a constant paddle speed, determine the speed of the river's flow. All right, so there's a little bit of physics going on here that I think is interesting, but also fairly straightforward. If you are in a river, the river's current is going to carry you along at the same speed that the current is moving. If you try to move upstream, well, then the speed of the river is going to slow you down. If you try to move downstream, the speed of the river is going to speed you up by the same amount. And so that gives us the tools we need. That, and also remembering that distance is rate times time, is everything we need. All right, if we call the paddle's speed v, right, v is a common variable for speed because really we think about it as velocity. And then let's call the river flow u, because it's a letter next to v. Then going downstream, the rate is your paddling speed plus the river's flow speed. And going upstream, your rate is the paddle speed minus the river's flow speed. In both cases, the distance is the same, 24. Going downstream, that's going to be v plus u times the speed, or the time it takes to go downstream, which was 3.0. Going upstream, the rate was v minus u, and the time it took was 4.0 in hours. using the distributive property here, I can rewrite this system of equations as 24 equals 3.0v plus 3.0u, and 24 equals 4.0v minus 4.0u. This is a system of two equations in two unknowns. We could either solve for the paddling speed, or we could solve for the flow rate, or even both. But we are specifically asked in this problem to determine the speed of the river's flow. We are specifically asked to solve for u in this situation. So as we approach using the method of elimination, we want to make the conscious choice to eliminate v and leave u, because we don't care about v. We don't need to know v in order to answer the question. That will save us some time. All right. Other than that, it's the same process we saw before. Let's call one of these equations a, the other one is b, and we're looking for a common multiple between 3 and 4. In this case, kind of 12 is my best bet. So I'm going to take equation a and I'm going to multiply by 4. I'm going to take equation b and I'm going to multiply by -3. That way the v's are going to be the thing that get eliminated. And let's see, 4 times 24. I think that's... There we go. That's 96. My calculator hates me, but that's okay. 4 times 3.0 is 12. And then 3 times 24 is 72, but we've got a negative here. So we've got -72 equals -12u. I'm sorry, that's a v, 12v, plus 12u. And when we add these together, 96 minus 72 is 24. 12v minus 12v is 0. We've eliminated v, which is what we said we wanted to do. And 12u plus 12u is 24u. Divide both sides of the equation by 24, and I get 1.0 is the value of u. I haven't been paying attention to units. I've just kind of been assuming that everything would work out. But if you go back to the problem, our distances have been measured in miles. Our times have been measured in hours. So I know that the units here of the rivers flowing are going to be in miles per hour. All right, so there we have it. A little bit of a taste of how systems of equations can be useful. Systems of equations are probably the most powerful tool that the mathematician has. If there is one thing that I hope that you know how to use moving forward, it's applying a system of equations to solve a problem. But I think this video has gone on long enough, so I'll wrap up here. As always, thank you for joining me, and I'll see you in the next one.